Welcome to Cassandra.Lunch number 137. Don't forget to like and subscribe, as well as turn on the notification bell so that you can get notified every time we post a video or go live. Today we will be discussing LLM fine-tuning with QLoRA, specifically dataset generation. We'll be discussing an overview of fine-tuning types and datasets, and this talk focuses on generating instruction datasets for fine-tuning. The co-organizers for this event are Rahul and myself. If you are interested in being a co-organizer, want to help get speakers by reaching out to people in the Cassandra community around the world, please drop me an email here or at the marketing email below. If you yourself are interested in giving a talk, please reach out to me, either for this lunch, Cassandra.Lunch, or for our sister event, Data Engineers Lunch. You can email us here at marketing or reach out to me directly at the email from the previous page. We are part of a larger community called Data Community DC, which believes in building an inclusive environment. So no matter your race, gender, or sexual orientation, everyone is welcome, and we expect respect to be given to all. Data Community DC is actually made up of a lot of different groups, generally centered around data, and you can find out more about all of the various groups and events at datacommunitydc.org. What do we cover here at Cassandra.Lunch? All things that talk and play well with Cassandra. We cover open source Cassandra enterprise variants such as DataSets, Scylla, Keyspaces, Cosmos DB, and Yugabyte. We also talk about tools in the ecosystem such as Spark, Kafka, and Airflow. I know Obi is going to be talking about Astra and some other of the tools around this spaces here too. If anybody that is new would like to say hi, what brought you here, or what you hope to get out of this, please drop something in the Zoom or YouTube chat. Here at Anant, we design, build, and manage global real-time data and analytics platforms surrounding Cassandra, Spark, and Kafka. So Cassandra is our bread and butter. Thanks to our sponsor, DataStax. Thanks to George Washington University for providing venue space when we have in-person events. And thank you to all of our institutional and organizational sponsors. If anyone has job offers, is looking for a job, please drop links and we will get them and put them straight in the YouTube chat. If anybody has any meetups, hackathons, classes, or conferences that you would like to promote, put those links in the channel as well. This is Cassandra.Lunch. We currently host it Thursdays at noon. We're looking for some other time slots to appeal to a worldwide audience. And our sister lunch, Data Engineers Lunch, takes place Mondays at noon. All of our videos are available on YouTube, starting with Cassandra.Lunch number 10. Also check out Cassandra.Link. Obi will actually be talking a lot about Cassandra.Link today. This is a hand-curated site for Cassandra resources, and you can really learn a lot about Cassandra on this site. You can check out our most recent public runbook, which is runbook 17, at anant.us/runbook. I will drop that in the chat shortly. And with that, I want to thank our speaker, Obi, for being here. And I'm really excited for this talk. Thanks, Obi. Really looking forward to it. And take the wheel.
All right. Thanks, Nick. Give me 1 second to share. All right. So as you heard, my name is Obi Anomnachi. I'm an engineer here at Anant. Today's topic is LLM fine-tuning. This is actually going to be a series of 2 talks on fine-tuning with QLoRA. Specifically, the model that we're starting with is Llama 2 7 billion, the 7 billion parameter version of the Llama 2 model. But today's talk focuses specifically on dataset generation. So we're actually going to skim over a bunch of the technical details about fine-tuning to focus on what data you need for specific types of fine-tuning, what types of fine-tuning there are, and how we specifically generated a data set that we could do fine-tuning with using data that we already had. And you can see in the sort of description under the title that we use GPT-3 and 4 to help us generate this. It's not fully generated by GPT-3 and 4. We have our own data coming in as well, and these specific instruction types which are generated by us, but GPT-3 and 4 are sort of integral into getting data into that instruction format that we'll talk about a little bit later. So starting off, what are we even talking about? What is fine-tuning? Why would you want to do it, etc.? So fine-tuning is a method of continuing to train an already pre-trained large language model. So a large language model, we'll talk about this a little bit later, but it's a transformer with attention that's trained on a huge non-domain specific unlabeled data set, basically as much text written by humans as you can possibly get your hands on for the pre-training, which, because there's so much data, is insanely computationally demanding. Only a few entities have the ability to actually train a useful LLM from scratch. But taking their starting point, it's possible to do some more training on your smaller, maybe domain specific, maybe labeled, maybe task specific data set and come out with a result that's better for your specific task while potentially being worse at some of the general other tasks that an LLM might be expected to do. So it's less computationally intensive. Specifically, in this series, we're going to be talking about QLoRA, which is designed to be even less computationally expensive. One of the reasons is because of the Q quantization. One of the reasons is because of LoRA, or low rank analysis, both of which are sort of modifiers on the fine-tuning process that make it cheaper to do in terms of computation. So fine-tuning used to be really popular as a method of teaching facts to an LLM. It turns out that it's not really suited to that as much as, facts or domain knowledge can be encoded within the documents that you use to fine-tune an LLM. There's no guarantee that it will produce factual information because of that. So fine-tuning as a method of teaching facts has sort of fallen behind RAG, retrieval augmented generation, and other systems where you explicitly provide factual information in a prompting step to a more general pre-trained LLM. Fine-tuning is more useful in shaping the output format, or say the method of speaking of an LLM. A lot of the time these days, people who are able to train their own LLM, so Llama, OpenAI, etc., will then take that LLM and then also release fine-tuned versions, fine-tuned for code, fine-tuned for instruction following, fine-tuned for question answering, all of these things that make it easier for users to use the LLM for their specific context that a pre-trained LLM is not necessarily good at. And fine-tuning is also something that comes up a lot in image models or text-to-image models like Stable Diffusion. People working with those models use fine-tuning to control their output in terms of art style, in terms of resolution, in terms of other variables that you might want to tweak. When we talk about fine-tuning methods later on, some of those will actually be more applicable to your text-to-image models than your text generation models. But all of them have their sort of places. All right, digging a little deeper into LLM architecture, how is it trained? Why can we continue to train it when someone gives us the model? So LLM models are transformers with attention. They're a type of neural network. You can see we take our input embedded text, and it goes through different layers. So each of these colored blocks over on the right are different neural network layers of different shapes and different values that do different things. So the main component of a transformer is a transformer block, which contains an attention layer followed by a normalization layer and a feed forward. You might also see it called feed forward. But essentially, attention comes from the paper Attention is All You Need, which sort of put forward the idea that just by having this specific transformer architecture with attention and training on a large amount of general data, you could have better NLP performance than a lot of the natural language processing models that existed at the time. That is sort of borne out in the way that LLMs are the big natural language processing model, and all other models have either been, replaced or subsumed by it. But basically, an attention layer determines which other words in the input sequence are important to understanding what word comes next. So an example that I've seen is, how does an LLM tell the difference when a user says bank between a river bank and a money bank? And that's by looking at the other words in the sentence. So previously, big NLP models that were used for things like text prediction in your phone when you're writing out text were Markov chains and other models that basically considered the last word and generated the next word. And transformers with attention still only generate one word at a time, but multi-headed attention means that they can not only take it into account more than one previous word, but also that they can scale the importance of those words based on how important they are to the meaning. So a lot of the input embedded words go through a positional encoding process and go through the attention process. So you can say that when you're looking at the word bank, maybe 3 words before is when you're talking about the river, and you understand that now this is a river bank because that word has high importance to the meaning and the other words in between don't. Like a lot of other deep learning models for image processing or adversarial networks and things like that, you build your transformer out of a bunch of different layers, blocks, with different structures. So the attention layer has a different, in this diagram, it's labeled multi-layer perceptron, but you might also see it as feed-forward layer or linear layer. So that layer is fully connected, whereas the attention layer might not be. It only takes into account words that come before and not the effect that the words that come before have on each other, only what effect they have on the next word. LoRa takes advantage of this structure. It freezes. So everything you see in this diagram in our actual training process that we'll cover next time is going to be frozen in place. Basically, none of these parameters are going to be changing. We're actually doing LoRa's for low rank analysis. It creates a matrix, basically another neural network layer with a rank similar to the layer that comes before it. So we put little LoRa blocks of neurons in between all of our big transformer blocks of neurons. And that allows us to change the outputs of the model while only changing a small number of parameters. And then the other thing that makes this training easier than what is called full fine-tuning, which would be take this transformer as is, load the entire thing into memory, and then put the entire thing through an optimizer with more training examples, which means you get out a model with weights that are completely different than what went in. And there's not really anything you could do to go back to the previous layer except load it from the file again. Whereas LoRa, it puts these little blocks in place in between the existing sections, and then you could theoretically remove all of those and end up back with the model that you had. So be able to use the old model or the LoRa trained model sort of interchangeably. And then QLoRA is special because it adds quantization to this process where groups of nearby neurons are treated as having the same value, effectively decreasing the total number of neurons that are available to be trained. So we'll see this in the next talk, but the main model that we're using, like I said, is Llama 2 7B, 7 billion parameters. But when we load it in using the quantization settings that we're using, we're actually going to see about 3.5 billion parameters. And those 3.5 billion parameters are going to be frozen in place. And what LoRa is going to look at changing is actually going to be like maybe a percent, 300,000-ish parameters that actually get modified by our training process. Okay, so we talked about what is an LLM, how do you fine tune one? You can do specific types of fine tuning depending on what data you put in. So the one that we're actually talking about here is instruction fine tuning, though we'll talk a little bit later about how maybe we're also doing some other of these. Instruction fine tuning changes the way that the model associates words. Well, all fine tuning changes the way that the model associates words with each other, but instruction fine tuning is meant to allow it to understand what to do in the face of specific instructions. So if you remember back to like GPT-2 days, the best way to prompt that model, this is, the field of prompt engineering was very new then, and people weren't really, it's definitely not as big as it has become. It was understood more poorly. But the way that a lot of people would prompt GPT-2 is that they would act as if there was sort of a break in a document that sort of described what came next. So they would say the following is an excerpt from a newspaper, trying to give it this specific voice by, insinuating that there is this existing document which we have part of, and we want you to generate the next part of this. Now, of course, you can still do that. LLMs respond to sort of patterns in language, and those patterns are still valid. But a lot of models, like for example, GPT-3 that formed ChatGPT, part of the difference between those two is instruction fine tuning, so that users can say, do X, and the LLM will actually attempt to do X rather than trying to figure out what the continuation would be in, say, an internet post or a book that contains the words do X. So that's instruction fine tuning. Transfer learning is a little bit weird because it exists for when you specifically don't have enough data, basically. So transfer learning, you fine tune on a minimum of data in order to create a small improvement over a pre-trained model. So this is something that you might do if you were working with a diffusion model to generate images, and you have, 10, 50 images from a particular artist whose style you want to emulate. And transfer learning would allow you to generate a model that will generate stuff closer to that. Transfer learning could also be a method of sort of defining terms. So in this sort of image scenario, if you fed in the prompt word dog, and then a bunch of pictures of the same dog or the same breed of dog or maybe the same color of dog, you could potentially get the model to understand dog as being closer to those images. So when you ask it to generate a dog as part of a picture later on, you would get something closer to those specific examples.
So, Obi, that transfer learning thing here, I'm having a little bit of trouble. You talked about it initially as a way to expand sort of the knowledge that a LLM has by sort of like extending the extending a small base of information into a larger base of information. Am I still thinking about that right?
No, not really. So
Okay.
transfer learning is about trying to teach the LLM something when you don't have a lot of data.
Okay.
So it's
So,
saying, I only have a couple of examples. but even these few examples should help you learn this.
Okay.
And please apply that to any future requests that I give.
Okay. So this might be sort of like in your toolkit of fine tuning. This is like something you would want to use during a beta release or an alpha release where you're trying to understand the behavior of your users and you're sort of feeding their behavior into your database and expanding from that using transfer learning fine tuning to like better understand their behavior while you still have a relatively small number of users.
Yes. Essentially, what you are doing is a small amount of fine tuning on a small amount of data to get a small improvement.
Okay, thank you.
Yes. So moving on, task-specific fine tuning, instruction tuning is a type of this where you have a decent amount of data, all to do with a specific task or a specific knowledge domain. So say you wanted to train an LLM that, speaks like the voice that's used in medical papers, um, or scientific research, or these specific domains where words mean a specific thing that's not necessarily captured in the large corpus of knowledge that the LLM is already working from. So it was trained to learn the generalities of the English language or whatever language you're working in. And here you want it to understand that specific words are used in specific ways with specific meanings, or that specific sentence structures are associated with specific behavior. So instruction fine-tuning is a type of this where you learn that the response to an instruction is following that instruction and not questioning it or starting an internet argument or whatever the LLM might do in response to someone telling it what to do. Or say asking a question, the response is to answer that question, not to ask follow-up questions, et cetera, et cetera.
So, Obi, that this type of training is pretty clear to me. But there is a question from the chat from Rahul that I wanted to ask. I think it's a little general here. Is it possible to train either LoRa or QLoRa modifications in the main model and then apply those changes to another similar model?
So provided the models have the same sort of structure, so the size of Llama 2 7B and Llama 2 13B are different, but the sort of blocks are the same. So it's theoretically possible to apply the same adapters from models with similar structures to each other,
Yeah. So,
but potentially going from, uh, sorry, Zephyr 7B or something, to Llama 7B might be. I think actually Zephyr is based on Llama, so that's a bad example. But going from GPT-3 to Llama 2, probably not doable. But even if you were to say do full fine tuning on your Llama 2 model, ended up with completely different model weights, you could then apply a LoRa adapter on top of that and come out with a different model.
and then you're essentially taking a layer with your QLoRa or LoRa fine tuning and just slotting it into the other model. You just have to make sure that the other model will sort of fit that structure, the
Yes.
structure of your model weights. Okay.
So it has to do with the rank of the matrices being, multiplied. And then, so the way we apply LoRa is that we attach the extra neuron blocks onto all of the linear layers in the existing model. So as long as you're working with a model that has linear layers in that exact same place, you should be able to slot the adapter on and off.
Thank you. And thank you for the question, Rahul. Okay, Obi, back to you.
Okay. What was I talking? Yes, task-specific fine-tuning. So task-specific fine-tuning So anytime you are doing extensive fine-tuning, so this is not just task-specific LoRA, but also task-specific full fine-tuning, you run the risk of something called catastrophic forgetting, where it forgets how to do things that it already knew how to do. So for example, if you were using an LLM to do classification tasks on just, let's say it's doing like a classic NLP classification task like sentiment analysis. It has an understanding of positive, negative, neutral, and you feed in your text and it gives you sentiment analysis on that text. If you spend a whole bunch of time fine-tuning this model to instead do, let's say, like keyword extraction on medical text, then you might come to find later on that if you go back to trying to use it for sentiment analysis, that it's now become really bad at sentiment analysis. And then one thing you can do to avoid this is to, rather than doing a single set of task-specific fine-tuning, you set up some multitask learning. And multitask learning is essentially task-specific fine-tuning for a number of tasks that you don't want the LLM to forget how to do. And we're going to see elements of this in our own setup because we're doing instruction fine-tuning, yes, but we also want it to be able to continue to do summarization and stuff like that. So some of those are in our instructions that are to be followed, making sure that, regardless of what the model learns from our fine-tuning data, it retains some of the abilities specifically to do with analyzing context that we want to keep in the model. And then sequential fine-tuning is, again, a lot like task-specific fine-tuning. Okay, actually, let me clarify the difference between multitask learning and sequential fine-tuning. Multitask learning, you build your data set, and it has more than one type of task or domain knowledge in it, so that the training process doesn't cause catastrophic forgetting because those model weights for doing those tasks are being reinforced. Sequential fine-tuning does task-specific fine-tuning in sequence, going from more general domains or tasks to more specific domains or tasks. So a single task-specific fine-tuning might get you from the general knowledge domain of an LLM to the medical field as a whole. And then in sequential fine-tuning, you would do another sequence of fine-tuning to go from the medical field as a whole to pediatrics specifically, and making sure that it understands the sort of medical jargon in that first set of fine-tuning, and then using that to incorporate knowledge about the specific field of pediatrics in the later steps of fine-tuning. So you could also theoretically go from more general tasks to more specific tasks in that same way, where you would say general LLM, then classification task, then sentiment analysis, and then maybe sentiment analysis of particular types of data. All right, talking about our instruction format. So we want to do instruction fine-tuning. We need specific instructions and specific results, even when the model is doing something other than instruction following in those instructions and results in that combined instruction set. So an instruction that tells the model to do sentiment analysis might say, analyze the sentiment of the following text and identify if it's positive. Not only are we telling it, this is the instruction, and then later on that gets added to, this is the context you need, and added to, this is the result we are looking for. Because fine-tuning, because transformers only generate one word at a time, we put this model through, and every individual instruction becomes essentially a number of training examples. So it will say, analyze the sentiment of the following text and identify if it's positive, and the first word of the text, and then predict what comes next. And then it will add the second word of the text on there and say, predict what comes next. The third word, and that's how the sort of training process goes, where it will learn to respond to instructions that when you say instruction, analyze the sentiment of the following text and identify as positive, not only should you be trying to predict the next word in order to encode the structure of sort of sentences and the structure of instructions, the structure of instruction following, but also make sure that it skills that sentiment analysis, make sure that when you are provided with context in an article that is positive about something, you are able to then follow, understand that you should produce the result that says positive after that. So like I said, we're sort of doing multitask learning at the same time as what we're mainly doing is the instruction following fine-tuning. So what we're trying to do here is avoid catastrophic forgetting, at least in those areas that we're interested in continuing to use. So we might find out later on, because sentiment analysis isn't actually something that we included in the dataset, that the resulting model isn't actually very good at sentiment analysis, but it should be very good still, or at least as good as it has been at summarization or at code analysis, or the other things that we're actually asking it to do in the instruction format when we are also teaching it to follow instructions that are given. Our instruction data set specifically is based around performing tasks on snippets of articles, specifically technical articles about Cassandra. Therefore, it's composed of instruction, input, and output sections, which all get merged together to become a single instruction. And even though, like I said, the training process is going to happen always one word at a time, because that's the way that transformers predict text, it's going to take into account all of the words that came before. So by the time it's predicting what the output section is, it's taking into account via the attention mechanism, what is the instruction, what is the input. Similar to the format of other instruction tuning datasets, in our case, the input field is always full because we always want to be relating back to an article about Cassandra that we're providing. And we can do a sort of comparison here. This data set, we're looking at Hugging Face, is alpaca cleaned, and it's 50,000-ish instructions and results. Some of these do have extra input, but some of them don't. And it's not always clear what's going to require an input section and what's not going to require an input section. For example, this one here, explain why the following fraction is equal to 1/4. Input says 4/16. You get an explanation, 4/16 is equal to 1/4 because they both represent the same value, et cetera, et cetera. It's giving an explanation just like you asked. But there is one here, write a concise summary of the following. So, and then it's an entire, snippet of an article about the Commodore 64. So this one, you could also put it in that same format. The instruction will be write a concise summary of the following, and then all of the following text would be moved into the input section. And you should get essentially the same result, but the alpaca data set comes from a lot of different sources. A lot of the newest stuff on here is generated by GPT-3 and 4. And a lot of the older stuff is handwritten, and it's called alpaca cleaned because the original alpaca data set needed to be cleaned. It wasn't very consistent. There were a lot of repeats and stuff in there that didn't actually fully make sense. So this is sort of the end result of that. And that makes it still a little bit weird. Not necessarily nonsensical because that's what the cleaning is for. But it can still be a bit strange in places and inconsistent. Okay, so where does our data set come from? So during the intro, Nick mentioned Cassandra.Link. This is a hand-curated knowledge base about Cassandra. All the articles in it are hand-selected, but obviously in order to present them to you here, we keep them all in the database. So starting from that collection of Cassandra articles, we are taking these articles and using OpenAI to turn them into an instruction dataset. So there are a bunch of topics actually in here. Just on here, you can see this one's about REST. The next one's about Node. Different ones about APIs and front ends and tools. And so there's a bunch of stuff. All of it is vaguely related to Cassandra, but a lot of it is very different. So an instruction that we tell GPT to come up with won't necessarily be applicable to every single article here in the database. So for that we get back is valid JSON. No guarantee necessarily about what that contains, whether it will have the keys you want, whether it will have the data you want, but it will be a valid JSON object. So you have precautions for all that stuff, and we'll see that when we look into the code in a little bit. So step one, we take the entire article. We attach it to our main article prompt, which has all of the instruction types in it. And basically, we ask GPT-4 of these, in this case, 14 instructions, which ones is this article suited for? So it might say, well, the output comes in basically just the prompt, the instruction type number, and the instruction prompt, and then in a list. Whereas, so it's not literally saying, okay, this article does not have a code snippet in it, so the analyzed code snippet is out. But it's basically doing that calculation. We tuned this prompt to make sure that we get minimal text back so that we could minimize the cost of using GPT-4. I think in this example, we incurred costs of like $20, $25 using GPT-4. Something like that, and then minor costs from GPT-3 since that's much, much cheaper.
Hey, Obi, for
Yes.
that cost, what's the numerator? So like how many articles did we go through at that price?
I want to say we went through 1,500, or no, more like 1,000. I'm gonna have to get back to you on the actual number there, but
Okay.
I think
Just trying to give the
total we
audience a sense of the
had
scale. Yeah.
1,500 articles, and I think we got through like 1,000 of them. So yeah, and aside on how many instructions you need, so when if we're talking about diffusion models, people do transfer learning on image diffusion models on like 10 pictures sometimes, for that marginal improvement. And that is possible. But for task-specific fine-tuning, the minimum that you want is probably going to be like 1,000 examples. And I think in this case, we're doing about 2,500 training examples, like of individual instruction, context, result sort of pairings.
Great. Thank you.
And obviously, the alpaca data set that we just looked at has 50,000. There are 100,000, et cetera, et cetera. So depending on how much fine-tuning you want to do, you're going to need more data, and you potentially run more risk of catastrophic forgetting, especially if that data set isn't constructed in such a way as to try and avoid that. Okay, what was I saying? So we get our results from GPT-4, and it says, okay, do prompt 1, do prompt 3, do prompt 7, and it has the descriptions of all those prompts in there. We want to use, in this case, I say traditional coding techniques. We use regular expressions to extract the numbers out from there and associate them with the actual instructions, which we have in a regular Python list. So we want to make sure, it's hard to tune even GPT-4 to give you exactly what you want in the format that you want at all times. So putting this back in Python allows us to take a couple of precautions so that we're not, the regular expression failing to parse 14, or say GPT gives back 13 and 14 with a space between them, but no other like separator. Things like that can mean that what we get back from GPT isn't exactly corresponding to the numbers that we want in order to associate them with a particular instruction type. But we pull out all of the valid ones. So even if it generates, like, say, this is instruction type 4000 when I only gave it 1 to 14, make sure that doesn't get through this filter. So we take each valid instruction type as determined by that code. We attach it to a main system prompt and then the full article text again. And we pass it to GPT 3.5 with our function calling stuff to make sure that the output is valid JSON. So one of the pitfalls of that function calling is that, empty string is something that it might generate if you don't tell it to generate JSON, or even the, empty curly brackets. So there are that, and then also, of course, the risk of running and getting JSON data that doesn't contain the keys you want or doesn't contain the data that you want. Some of our early prompts had this sort of issue. Let's see. Am I sharing the full screen or am I sharing?
Right now, I'm still seeing. Yep, now I'm seeing your notepad.
Okay, so this is the results
Although
of.
the text is a little small. Can you expand it a little bit for us? Thank you.
So this is the result of an old version of the inner prompt. Well, the outer prompt as well. But basically, we were telling it to do specific things to the articles, but we weren't really getting out valid stuff that we wanted. It was in the JSON format just fine, but if you look at it, our prompts still need tuning here. You can see that the input, the context that we're getting is particularly short, not necessarily capturing the nuance of the articles that we're putting in. And then say something like this. Classify the steps involved. So this is obviously from an article about adding a new data center and commissioning an old data center in a Cassandra cluster. And the context that it's pulled is step 1 of that process. And because it only has that little bit of context, it can only say, I guess these are the steps. So you can come up with a prompt and you can use the function calling to get back JSON and still be short of what you actually want to get. These are a little bit better, but we'll see when we run our examples in a little bit that we had to mix up these prompts a little bit, specifically the system prompts, to make sure that we are getting out appreciable amounts of data in the input and then actually generating the output based on that, so that it's from an actual snippet of the article and not just a summary of information. All right. So time to move on to the demo. This is the repo. It has the full fine-tuning notebook in it. But what we'll actually be doing today GitPod. We're going to be focusing on our code to generate the instruction training set. So until this comes up, I actually wrote a custom notebook as a demo, but this code
Can you
does
blow that
nearly the
text up
same
for
thing.
us a little too?
Sorry, what?
Can you expand that text for us a little bit too?
Yes.
And just to confirm, this is, as you guys can see, this is a public repo. You can all access this code.
Yes. So this is the actual code that does the instruction of the generation of the data set. There's a custom demo notebook that I wrote for this demo that when GitPod opens, we'll be able to use that specifically. But to get started, we can just look through this. So the first thing that we do is do our imports. You can see there's no Hugging Face stuff here. So we're not actually loading in our model for fine tuning. This is all about the prompts, the data, and OpenAI. So we have AstraPy to connect to Astra, where our data is being stored. We have OpenAI for the OpenAI models. In this case, we're using the OpenAI Python package specifically because it makes it easier to do the function calling. We could otherwise be using LangChain or Llama Index or any other of the frameworks that sort of standardize interactions for different AI packages. FTFY is for fixing text because we've just downloaded a bunch of these articles and curated them, but that doesn't necessarily mean that their formatting is understandable. Instruction prompts is our Python file that contains the prompts. We have rev for regular expressions, OS, and .env for loading in our tokens and such from the environment. Okay, so we load in, this is Astra stuff, the token and endpoint for connecting data stacks Astra, Ocean API key, and then our collection names also for Astra. We create the Astra instances to connect to the collections. We actually create the output collection if it doesn't exist. And then stuff for pagination from Astra. So Astra limits you to 20 results per request with pagination in order to get the next 20 and the next 20, et cetera, et cetera. Okay, so our first function, get instruction types. This uses the GPT-4 along with our prompt in order to get back a response. So basically, all it does, it takes in the article. This is just the text of the article. There's no extras in there. And then we pull our prompt from instruction prompts, combine it with the article, we pass it to GPT-4, and we get the response. And if we look at the instruction prompts, here's our main outer prompt. This prompt should act as a classifier step in larger goal to create an instruction set, fine-tuning. So first we set up sort of the meaning of what this prompt is supposed to do. It's saying generate an instruction. The instruction is supposed to be something a user asks the LLM. The context is something from the article, and the response is something that an LLM would generate in response. We have pretty extensive system prompt up at the top. to get, make sure we're getting out or defining the task that we wanted to do in enough detail. And then we say, okay, here are some instructions that every article that can be reviewed will probably be able to do. Summarize a section of the article, describe or summarize the impact of the article. So every article contains content that can be summarized. Every article has some place in the sort of larger constellation of information about Cassandra. And these instructions may only apply to certain articles. So explain any caveats or cautions noted in the article. If it says not to do something, explain why. Clarify configuration options. If there are options about what to do presented in the article, explain each one and what they do. Explain or summarize the feature. Explain a technical concept. Analyze and summarize a code example. Obviously, this one only works when there are code examples. Compare and contrast two entities. Obviously, this only works if there are two entities. Provide practical advice. Summarize the impact. Describe integration impacts. So if you already have an ecosystem and you introduce this new tool into it, what are the potential impacts? Describe compatible technologies. Describe a practical use or help me implement this. And then there's more boilerplate telling it what to do and what not to do. And then we say, okay, here's the article. And then this line here actually is telling it to basically produce as little text as possible. Only say, for clarify configuration options, if for is applicable to this article. And then we combine it to the article and we get our response. Our next is just regular programming, extract numbers from our instruction types response. So the instruction types response looks like a list of, pieces of text. So it will say one, and then the definition for one, which is summarize the section of the article. And the next thing in the list will say three, explain any caveats or cautions. It's a single piece of text, but we split it into a list, and then we remove all of the actual text there using this regular expression here. And then we say, so the regular expression basically just splits it up. You end up with a list, some of the things of which are numbers and some of the things of which are text. And then we say, if it's text, you can drop it. It says if it's a number, you can keep it. And then if the number isn't between 1 and 14, in this case, I think it's 0 and 13. In this case, then also toss it. And return me a list of just the numbers. And then those numbers get associated with this list of prompts here, where we have split out all of these potential instruction types into an actual prompt, and then taken all those inner prompts and put them in this list here, so that they in order, so that they can be corresponded to by number. Aha. All right, we have our actual notebook up. So this is going to be a lot of the same stuff we just went through. Do the imports. Oh wait, not yet. Here, rename. .env. Put the actual stuff in the env file. Okay. Now when we load the DNV, we should get true. Set up the connection, just like we said, to Astra, to OpenAI, etc. This time we only have the in collection name because we're not going to actually be writing the output to Astra. Initialize the connection to Astra DB, set up the initial state for pagination, and then back to our functions. Get instruction types is exactly as we just saw. Extract numbers is exactly as we just saw. Generating instructions is the inner loop of this. Well, it runs in the inner loop. What it does is it takes a specific instruction number and an article, and it combines that with the system prompt and the article, and sends that to ChatGPT, specifically looking for response type as a JSON object. And this is still a chat model, so you must specify the system prompt as well as the user prompt in messages that match that sort of chat model, and then look for a response. Did I actually run these previous two? Yes. Okay. So now we pull an article out of Astra and we look at it. So this one is about executing multiple concurrent requests using the C# Cassandra driver, the C# DataStax driver to connect to Cassandra. So basically the article just talks about how to do it. It has stuff about, instructions, starting a cluster, instructions on using .NET to actually run your files, et cetera, et cetera. We run it through our outer query, and we get our chat completion, and it says, content says, 1, summarize a section of the article. 2, describe or summarize the impact of the article. 7, analyze and summarize a code example. And 14, help me implement a tool. We can run this through the code at exact numbers, and it says, 1, 2, 7, 14. And then this code pulls out the instruction numbers and then grabs the instructions and runs them through the function from earlier that fills those out. And this takes a little bit to run because it's doing 4 separate function calling requests to GPT-3. So wait for this to run, and we get, so when we put these things into Astra to later pull them to construct a dataset for fine tuning, we want to associate them with the correct article ID. This is the article ID from the Astra table that already contains the article, in case we want to change up how we're doing this. Say if we wanted to have the input field replaced with the entire article and not just the section of the article that we wanted to talk about here. But we pull a section of the article, we have our instruction that it has filled out with detail. So the instruction is summarized, but what we get in the instruction field is summarize how to execute async concurrent requests in Apache Cassandra using the C# DataStax driver. So rather than summarize the article, we're getting this context, which helps us execute this specific instruction. And then we have our output that tells you how to do it. And we got rows for, this is 1, summarize. This is 2, let's global. One, summarize. 2, explain. 3, analyze the code snippet. And then 4, tell me how to implement this. And it gave us instructions. So this is how we generated our results. So the Cassandra.Link database has, I think I said about 1,500 articles, but we get, in this case, this one article provides 4 instructions, but some of them provide like 9 instructions, 10 instructions, maybe the full 14, depending on what the article is about. But in this manner, we can go from our 1,000 articles, however many we process, up to an amount that's actually sort of an appreciable fine-tuning data set to be processed. And that is what, and how we did that is what we're going to cover next time. So that's
Thank
about
you
it for
so much,
today.
Obi.
Back to you, Nick.
Yeah. So again, I want to reinforce the sort of context that Obi's given us here about what stage in the process this is at. So in the fine-tuning process in general, we sort of normalized the data set, the Cassandra.Link data set that we were using. We did an analysis of each article using GPT-4 to tell us which instructions to generate. And then we used GPT 3.5 to generate the instructions. And we saved them in, are these saved in Astra right now? The
Yes.
instructions we generated? Yeah.
Yeah, the articles and the instructions are both in separate Astra tables.
So now that we have the instructions, this is what Obi was saying. Now we're ready to actually do the fine-tuning process based on this instruction data set. We're essentially giving a new set of instructions to the LLM, and it's going to change its weights based on those instructions. Do I have that all right?
Yeah. Well, because we're using LoRa, the weights of the model itself pretty much stay where they are,
That's
and
right.
only the added stuff changes.
Yeah, we're adding a new layer of weights. Cool. Well, thank you everyone so much for your time. This was a really exciting talk, and I'm really looking forward to the next one. Thanks so much, Obi. And everybody, have a great rest of your day, whether you're watching this live or watching this recorded. Bye. Okay, the stream is done.